Okay, so we're going to talk about the strongest attractive force first, which is ion-ion. And so this is going to be present in all ionic compounds. So if you see an ionic compound, it has ions. They are attracted to each other with ion-ion attractive forces. So if you see a metal and a non-metal, ion-ion attractive forces. You see a polyatomic ion, you know you got ion-ion attractive forces in there. So, if you see an ionic compound, it's going to be a candidate for strongest. You see two ionic compounds, though, and you're comparing a group of molecules or compounds. How do you know which one has stronger attractive forces? Well, greater ion charges equals greater, whoops, not like cheese grater, but greater, like Greater Lakes greater. Greater ion charges equals greater attractive forces. And then the other tiebreaker is smaller ions, so that means they're closer together. That equals greater attractive forces. And we're going to do some examples with this. Alright. So, for example, we got NaCl versus, what do we do? MgS, magnesium sulfide. Sodium chloride, magnesium sulfide. It's not my class, I'm not working NaCl in there somewhere. Alright, so we can look at our periodic table. We see we got metal, non-metal, metal, non-metal. So they're going to all have ion-ion attractive forces. So they tie in terms of what attractive force they have, but how do they rank within that attractive force? Well, if we look at our periodic table, we can see that this is going to be a plus and a minus. This is going to be a +2 and a -2. So this has the greater ion charges. 2 is greater than 1, right? So 2's are greater than 1's. So this will have more attractive forces. It'll have more ion-ion attraction because it has larger charges. Alright. Now what if we have something like, do I have enough room actually to throw that away preemptively? Yeah, we'll do one more on this page. Why not? Let's say we have LiCl versus NaCl. Okay. So in general, larger charges are going to win. I'm not going to play around with like, oh, they're so small that it offset it. So first look for charges. But what happens if charges tie? They're both ones. +1, -1, +1, -1. So what do? You look at your periodic table. And remember that as we go further up rows, the atoms get smaller, the ions get smaller. And so lithium is in the third row and sodium is below that. So sodium is going to be larger than lithium. So lithium is going to be a smaller ion. It's going to have greater attractive forces. So lithium is smaller than sodium, lithium ion. So that equals more attractive forces. So it's going to have stronger attractive forces because it has smaller ions. And it'll always be that clear cut. It'll just look at rows. Smaller number of row, smaller sized atom and ion, because there's less shells of electrons around it. As you get less and less, the shells get smaller and smaller, which means the ion gets smaller. So it's defined by the size of its electron shell. And so as the electron shell gets smaller, so does the atom and the ion. So that's simple. Because remember, volume is the electron cloud. So what you look at is an ionic compound. Okay, is it the only ionic compound? Ding, 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 you got a winner. Are there multiple ionic compounds? Okay, Well, which one has larger charges? Winner. They tie. Smaller ions, which is a little trickier idea. So just get comfortable reading the periodic table and making sure you understand smaller ions. So smaller atoms equal smaller ions. We talked about that trend earlier when we talked about like electronegativity and stuff. So it's not a totally new idea. It might just be a little bit rusty. So just brush up on it. And that's all you got to do. And we'll practice kind of everything more in the very last video for this section. But this is how you can decide between two ionic compounds which one has the larger attractive forces. Okay, so next we're going to talk about hydrogen bonding and just kind of carry through.